Hello everyone, today we're going to do an experiment. We're going to use an old school ray box like I have here, which is producing 3 parallel lines. Okay, so they're not quite parallel, but that's some measurement error. We'll talk about that later on, but imagine they are parallel. We're going to treat this middle one to be the principal axis, and then this one and this one will be parallel. We'll put it through a diverging lens, and then we'll use some geometry and some calculus to work out the focal length. So let's go ahead and place our lens in the rays, and there you can immediately see that they diverge. Okay, so they're not diverging a lot, but they're definitely diverging, and I'm going to make some marks on the paper here so I can see where those rays are. I'm then going to trace around my lens so I have it as a realistic geometric image on my bit of paper, and I can take measurements from it. Okay, there we go. Let's take some measurements at the more markings at the back here that we can take measurements from. And that's about it. Now we just need to do our drawing. Okay, so our drawing looks like this if I connect all the dots together. And I'm just going to go ahead and extend these lines backwards, if you like, into the negative direction. This is the behind the lens, but this is where our negative focal length would end up being, because we're producing our image over here. So these dotted lines are going to give me a value, a single value for the focal length that I'm going to just straightforward measure on this page, and then we can use that to compare to our calculated values. Okay, so here's a not to scale schematic, just so we can talk through the geometry that we're going to use here. Once I start collecting my data, I'm going to actually just go ahead and straightforward measure this focal length here. That's going to be our reference point. But then we're going to use trials up to, I think we've got 6 trials here, to take measurements along here. And that's what we're going to use to get a slope on a graph, and then we can use the slope of the graph to get our value. I'll show you how that's going to work. Just to remind you at this point that we're using the thin lens equation, so all of my measurements will be coming from this black intersecting mark here. So in other words, the middle of the lens. In thin lens equation, we ignore the thickness of the lens, so that's not part of our calculation. And then, of course, what I'm going to be referencing here is going to be the focal length, which is going to be from here to here. And I should be able to just draw that in right here. This is going to be my focal length right here. I'm going to need that. My trials are going to be the distance to each of these images. And you can kind of imagine, if you like, that there's a screen. If I first of all place a screen here, this would be obviously the distance from the lens to the screen. That's going to be the distance of the image in trial 1. Then I'm going to do it again for trial 2, and so on. And I'm going to take a measurement of this value here. Let me put it in. Yeah, I'll use this one here. I'm going to put it in here. This value here, let's use a ruler. This is going to be an important value right in here, and I'm only going to do it for this trial here. This is going to be the height of the image. I'm going to do that for each of the trials, and then of course I've got this value in here which I'm going to record, which is all the way across here. And again, I'm just doing this for the oops, I've gone too far there. I just want to go to here. This distance from here to here is the distance to the image. Okay, hopefully that makes sense. Okay, okay, so we're going to think about collecting data. I've already kind of given it away, in that these are my trials. These are going to be my manipulated values. I'm going to change this DI for each trial. So if I'm going to start collecting data in a data table, my DI is going to be my x-axis. I'm going to put that in my table here. So this is going to be my DI. Let's put it in centimeters. And then my responding variable, the y-axis is going to be, well, think about it, what's going to change as I increase this distance? Well, hopefully you can see what's changing. Well, on trial 6, there's a difference there. Compared to trial 3, there's a difference there. And so it's the height of the image. So my y-axis is going to be the height of the image in centimeters. Okay, and I'll show you my data in just a moment. Okay, so one other thing that's important is the geometry just of what we can see here. I'm just going to point something out for you here with a highlight. I'm going to go from here all the way along here. There should be a straight line, obviously. Let's just go to the number 6 trial for now, to here, and then again, I should be using a straight line, but I'm not. There we go. What can we see here? Well, if I make it even more clear, hopefully you can see there's a triangle. And if I was to make a statement about this triangle, I know something about the, let's just indicate it on here. This is going to be the opposite side of the angle there. This is going to be the adjacent side of the angle there. And if I'm interested in theta here, well, I'm going to say that tan theta is equal to opposite over adjacent. So opposite over adjacent. And what's opposite? Well, opposite is the height there. And the adjacent is di plus f. Okay. All right, so I'm bringing into shot here the data that I've collected from my paper drawing, just using a ruler, and I've put it into Google Sheets or whatever spreadsheet we choose to use. I've graphed it as a scatter plot. We'll talk about how to get, we'll talk about the slope values and such in a moment, but let's just think about what we're doing. Okay, so here's my data. My x-axis is the di, the distance to the image, and my y-axis, this one here, is the height of the image. Now, you can hopefully see that this is my data as a scatter plot. Let's just move that in a bit there so you can see. There's my data as a scatter plot. And you can see that there's clearly going to be a y-intercept. And then if we traced it all the way back, there'd be an x-intercept too. Now, those are going to be useful because maybe some of you have spotted this already, but if I bring back in this image that I had at the beginning, and it's kind of overlapping here, but bear with me, bring this back in, this graph is literally a representation of the image itself. So remember that I'm plotting the HI, the height of the image, over the and the DI. Well, both of these are almost forming the graph itself. You've got the middle of the lens is the y-axis, and then this would be the x, and this would be the y. So this is almost, the graph itself is almost a sort of reconstruction of the diagram itself, and that means that we have some significance to the x-intercept. So I want us to keep this in the back of our mind. The x-intercept is probably going to give us an indication of the focal length. But that's not what we're going to do. We're going to take a slope value, and we're going to use slope as well. So at the moment, we're playing around with 3 different ways of getting, the focal point, the focal length. Okay, we are just going to go ahead and just make a measurement on my drawing. I'm just going to take a straight measurement. I'm going to use the x-intercept because my graphing looks exactly like, it actually comes from the geometry of the picture is making the graph. But then perhaps more interesting, we're going to get a slope. We're going to get the slope value. This is what we always prefer to do because it gives us this averaging power, smooths everything out. Any variation in the data gets cleared up by using a slope. So let's take a look at how we're going to get that slope. Okay, so remember on our original diagram, we'd made the statement that tan theta equaled the height of the image over the distance the image is away plus the focal length. Okay, so let's, and we'll just make it another point here for saying that on our graph, the y on our graph is the height of the image, and the x on our graph is the distance of the image. So when we try and overlay this on our y equals mx plus b, because we do have a straight line graph, we're going to try and overlay this statement onto it. We're going to be looking to solve for hi. So let's do that. Let's take this equation and simplify it down and solve it for the height of the image. Okay, so height of the image, which is on the y-axis on our graph, is going to be equal to tan theta times di plus f. So now I have to factor that out. So I'm going to say that the hi is equal to tan theta di plus tan theta f. Okay, so now we can just do our little overlay that we're used to doing. We're going to take this statement here, which we've said from our geometry, and we're going to bring it up here and try and overlay it onto our y is equal to mx plus b statement of a straight line. So we'll just bring back the graph that we originally drew just to highlight that and remind ourselves that the height of the image is the y. Okay, so that's our y part of our graph. And then the distance of the image at the bottom here, that's actually going to be our x axis. So we can hopefully do this mapping now where we just kind of go, okay, that there is good. That's my y part of the graph. And the x axis, well, that's the di. So that means that the slope, let's make this statement now, m is equal to tan theta. Okay, and then b, the y-intercept must be equal to tan theta f. I'm going to write that in here. B is equal to tan theta f. And this is where we do some equivalencies, because we're basically saying now that slope is equal to tan theta and the y-intercept is tan theta f. Well, check this out. If the slope is equal to tan theta, then these statements are interchangeable. So I can therefore say that b is equal to mf. In other words, the slope f. So b is equal to slope of the line f. In other words, the focal length is b, the y-intercept, over the slope. Okay, so when we analyze the data, here's our graph, our original data plugged into a graph. I just chucked in a line of best fit here so we can see it intersecting here with the x-axis. This would be, of course, this is the x-intercept, which we've already sort of shown that because this graph essentially matches the geometry of our diagram, this x-intercept is the focal length. And so when you get the x-intercept using the software, you're going to get, there we go, 9.6. And it's a negative, of course, because it's to the left of the lens. It's behind the lens, if you like. So that makes sense. It's a negative. Now, what do we get? We really want to look at what our values give us based on our formula, our interpretation of the formula there. And here it is. When I do my y-intercept divided by the slope, there it is. Look at that. It's it's the same number, surprise, surprise, because, hey, it works. And so this just shows us that using our software from my data, I get 9.6 as my focal length. Now, of course, I can't eliminate all the error, and remembering back to the beginning of the video where I was making my measurements on my ray diagrams, of course, they weren't that easy to get exact, and so there's going to be measurement error all the way through this. When I look at my original paper drawing and I take an actual measurement using a ruler, my measurement is 9.1 centimeters. So again, not too bad. In fact, about a 5.3% error there. Okay, so that's about us for today. Look for a follow-up video where I will try and do an intersecting chord theory. This is really just where you take mathematical principles of a circle like this, and if you have a chord that runs through it, something like this, run it through right there, then you can make a whole bunch of statements about it. Or you'd put probably one like this as well. I'm not going to get this right, but there we go, something like this. Make a statement there, and you can start making some, you can say, well, this is A and B, this is C and D, and you can make a bunch of statements. And of course, what we're referring to here is that the intersecting chord theory, as we'll hopefully show if I do this next video, is going to help us because this part of the circle represents the diverging lens. Okay, so if I was to draw that diverging lens on here, it might look, oops, not with this, it might look something like that, right? And so if we use our intersecting chord theory and we can work out the radius, and if we know the radius of a circle, we know the radius of curvature, and that will tell us something about the focal length.